So that's all regarding this. Next, we'll talk about some slide between the thermal conductivity. So you have got the idea of the thermal conductivity, how it is coming. So the effect, which is Q that you take here, is minus K that is the general equation we write it. So this K is the thermal conductivity. Is it already you have told it, it's a thermophysical it's a thermophysical transport property. So thermal conductivity is a thermophysical transport property which relates to heat transfer, heat conduction, which relating to heat conduction. In between the cause and effect. That's why it's a transport property, like a viscosity. Viscosity, if you remind this thing, viscosity, what was the Newton's law? Stress is equal to viscosity, dynamic viscosity, into the rate of strain. Remember this thing in one dimension only, I'm writing it, not elaborate this thing. So it is the cause and effect relation was set up in this way. Because of the stress, strain is occurring. Is the cause here? Because of the strain, stress, strain is occurring. That is another constitutive law. This kind of the properties are all of the transport properties. Another transport property is the diffusivity. There also the concentration gradient. One higher concentration, one lower concentration. If you keep it, flow will be takes place. Mass flow rate will be takes place. Similarly, the diffusivity also another transport property. Diffusivity. Viscosity. Thermal conductivity, all of the transport property. It is the relates between the cause and effect. All of this. That is the relation here in between these two. So already I have told it regarding this cause of the heat conduction for the solid. Cause of the heat conduction for the solid already we discussed. That is the solid two parts. One is due to the free electrons. Free electrons for the metals. That is the physics behind it. And for non-metallic, the lattice vibrational energy wave propagation. That is for the non-metallic. Non-metallic, there may be the two parts. One is the crystalline, like the graphite, like diamond, quartz, crystalline, and another is amorphous. Amorphous is the glass. In the glass, two molecules, there is a void. So it cannot transfer the energy. So that's why the thermal conductivity value, K value, is less. K value is less. As it is a crystalline, the lattice vibration energy propagation is very high. So K value is very high. In case of the, we'll see the values also, how much values for the lattice vibration energy for that case, this case. For the liquid, cause of the heat conduction is the molecular momentum transfer. Molecular momentum transfer. That is the reason. Cause. In the liquid, the marker is the best student. It getting the highest marks. Cream student like it. If the thermal conductivity of the marker is the highest. Highest for, in the case of the liquid, the marker is the giving the best conductor. That's why we use the mercury in the thermometer. That's why we are using the mercury as a thermometer. Okay. For the case of the gas, molecular momentum transfer, same cause. Molecular momentum. But in case of the gas, if you increase the temperature, the molecular randomness will be increased, collision will be increased, thermal conductivity also will be increased. You can see in case of the hydrogen, if you increase the temperature, the thermal conductivity will be very high. The graph will be very high with the temperature. Conductivity, and if you draw one conductivity versus temperature, you will see if you increase the temperature, you will see for the hydrogen that it is rising in this conductivity in case of the hydrogen. Then next is the helium, rising in this way. Then, yeah. But it will increase. It will increase in this fashion. Because temperature increase the velocity, RMS velocity, according to the kind of theory of gases, root T. C values root T. Similarly, it will increase the randomness, it will increase the collision, it will increase the thermal conductivity. These are the example how the thermal conductivity is increasing in the fashion. Here, which is increasing? Thermal conductivity is increasing. Initially, the thermal conductivity at atmosphere, at normal temperature, we are talking about here. The hydrogen, helium having the poor conductivity. The poor conductivity. If you increase temperature, the conductivity will be high. It will become a good conductor. But at normal temperature, hydrogen, helium is a very poor conductor. Then insulator. In the insulator, what we are using? Fiber, wood, foams. In these things we are using there. Then for the case of the liquids. In case of the liquid, which is the best thermal conductivity we are getting? For the mercury. Liquid, the mercury having a very good thermal conductivity comparative to others. That's why we are using mercury in the thermometer. In the metallic, non-metallic solid like rock, oxides, these are the non-metallic solids. It is covered. Then metal alloys. So you can see pure metal, thermal conductivity of the metals is more than the metal alloys. You can see here. Here aluminum also will be there. So thermal conductivity of the metal, pure metals, having more than the metal alloys. Then coming the non-metallic crystals, some crystalline material. diamond, graphite, silicon, quartz, it's having a higher conductivity than pure metals also. But 70% is covered. Thermal conduction is done by this pure metals. 70% as per example. Some idea is what is the value. It will give you that good clarity regarding this topic. Asbestos, which we are using as an insulator. Asbestos we are using as an insulator. Asbestos, glass wool. These are the insulator we are using as an insulator. The thermal conductivity is the less than 1. 0.2, 0. Glass wool, you can see glass wool in the turbine. We are using the glass wool for the insulating purpose. So very poor conduction will be happening because of it. So you can see the thermal conductivity value is very less amount. Polyurethane foam, which is using in the refrigerator wall, it is not allowing to comes heat inside to the refrigerator. So there also very poor conductivity should be there. It desire poor conductivity. Very less amount of values. Refractory brick. It is also as an insulator we are using, because in a furnace, the some brick we are using that can withstand the high temperature, as well as it will not conduct this heat to the outside surroundings. These two desire is there. That's why conductivity should be less. Air is a very poor conductor. Air conductivity value is also, but temperature if you increase, this value will be increased. It is at ambient temperature. Water is also very less. Poor conductivity is there. Heat conductivity for the case of the water, that is this one, 0.63. Water conductivity is 0.6. Then coming into the mercury. Mercury is the highest in the liquid. Is the highest, 8.43. Highest K for any liquid. Mercury. Then it is coming for the metals. Steel, aluminium, copper, silver. It is increasing in nature. You see, it is increasing. As per this, all cases is due to the free electrons. Because of the free electrons or valence electrons. Abundant electrons at the outer periphery of the atom. So it is jumped from one atom to other atom. It is carrying the heat. Then the diamond, you see the non-metallic one substance form of a carbon. It's having that is the 2300 watt per meter Kelvin. But in the thermal conductivity, we discussed watt per meter Kelvin. What is the unit of the thermal conductivity? We are not discussing. This thing we are just seeing one times. What should be the unit of it? All unit in the sense. So heat flux unit. So heat flux, we are telling about the rate of heat transfer divided by the area normal to the heat transfer. So rate of heat transfer is the joule per second or watt divided by meters. So better to write it down. Heat flux unit is the watt per meter square is the SI unit. Temperature unit we all know. You can use Kelvin, you can use centigrade, SI we use Kelvin, whatever it is. Temperature does not concern in that case. What is the unit for the thermal conductivity? K. So unit for the K is the unit of Q and unit of temperature gradient. Is the temperature gradient? What is that? This is nothing but I del T del X plus J del T del Y plus K so T divided by length. So this is coming watt per meter square. This is coming Kelvin per meter. Now centigrade, degree centigrade per meter. So ultimately, the unit for the K is coming, unit for K is coming watt per meter second, meter Kelvin. SI unit. Watt per meter Kelvin. SI unit. Here, whatever the values is given in the sense of the watt per meter Kelvin. So that is the unit for the thermal conductivity. Watt per meter Kelvin, or you can write it down the same values, no changes there. Watt per meter degree centigrade. Unit for the thermal conductivity.